Once you've done all the previous steps, merging, cleaning, visualizing, then you're ready to do the data mining per se. So what does that mean? It means that you will be able to use already existing method and algorithm in order to really focus on the data you have. So depending on the language or software you will use, different libraries will be available, and you will have to choose, using the expert intuition, the most adapted to your data and to the kind of information you want to obtain from this data mining. So, for instance, if you are looking for association rules, you will be using the Agraval algorithm. It is the most frequent algorithm which will be embedded in the software you're using. What is this objective? The objective is to find a phenomenon that happen at the same time, that you can find together in the same specimen. So for instance, is what kind of product are bought at the same time when you are doing your shopping? What kind of drugs work better for depending on DNA of the sick person? Those kind of things. What are the phenomena that you can find together? So here are the different performance indicator of the method and how it works. So this method was used in the early beginning of data mining in order to identify which products were bought together in shops. The objective for the shop's owner was to put them as far away as possible in the shop so that a customer will have to go through all the store before finding the objects they wanted, the items they wanted. The goal was that they were looking for item A and B, but maybe on their path they will find products that they didn't need, but they will buy them anyway because they are going through them or in front of them. So one of the most famous association rules that was found in the beginning of data mining use was this funny association rule, which is that on Friday or beginning of the weekends, most people who buy baby diapers will also buy beers. So this is interesting because then you know that when you are designing your shop layout, you will put those two products as far away as possible, so that when people buy diapers, they have to go through the clothing section, to the fruit section, to the frozen goods section before coming to the beer section. So they might buy something else. So once this rule was found, experts tried to understand them, and the explanation of this rule is that when you have young children, you tend not to go out so much because you have to stay home to take care of your children, but you still want to enjoy apéro, so you buy beer to drink it at home. So this is an explanation, but it was firstly found when looking into data. You have to be careful to some specificities of these association rules. A strong confidence in association rules doesn't mean that there are a causality between the two phenomena. It does not explain why the two phenomena are being observed at the same time. So it is not because you have bought diapers that you will have to buy beer. It is not a causality, but it's something that you observe at the same time. So be careful on how you use this rule to make decisions. And association rules are quite easy to find. The algorithm is old, so it was enhanced. And so nowadays, when you use association algorithm, you will find a lot of rules. So to sort them, you might need experts that will identify what are the interests of the different rules, and it will help you in addition to the statistical KPIs from these methods. Another way of using data is to classify specimens. So you can use present data to understand more what's happening now, but also to, this is useful when the data are not labeled. So you have a lot of specimens and you don't know how to sort them. Then you will use classification using unlabeled data to define groups. But you can also use classification from today's labeled data to predict further and future behavior. So there is two stages when you are doing prediction. The first stage is the creation of the model by a learning phase, which will rely on the use of a labeled set of data. And you will model those existing data using rules or decision trees or formulas explaining the relationships between different characteristics, for instance. And then, once your model is built and tested and you know it is reliable, then you can use it to predict, to classify new entries, new specimens. So each time you have a new entry, you will be able to predict in which groups it belongs. Of course, in order for your model to be sound, to be reliable, you have to choose very, very carefully the learning set. How can you measure that your learning set is appropriate? So first of all, it must be representative of the reality. You have to have the same diversity as the real phenomenon. So your data set must be a small picture of the whole world. And also, you have to be able to detect outlets in your learning set. Because if you have a small set to learn, any outlets will generate rules very specific to those specimens that you add in your learning set, and it will be useless to describe the bigger world. Then you have to, of course, to evaluate the performance of what you've learned. In order to do so, you should have a test set, which is different from the learning set, but should also be labeled. And using your prediction on this test set, you will be able to evaluate if your prediction is right or wrong. What you are interested in is to find sound information. For instance, if you are looking to know if people have a specific illness or not, then you will be interested in finding true positive, so detecting the people that you are saying are sick and are really sick, and the people who are sound, healthy, and are really healthy as predicted in your model. So this is the thing that you are interested in finding. And of course, false positive and false negative, you want to avoid at all costs. So this is a way of identifying if your classification is right or not. You build your model on a learning set, and then you test it on a test set before using it on unlabeled data. So you can use a complex or simple classification method. The easiest way to classify is by making a binary classification, like the one used here. You have only two categories, sick or healthy, and then you will have to assess which specimen belongs to which groups. So you can do a linear classification based on one or two characteristics of the specimen, or you can do more complex classification. One kind of defining how to build these different groups is by using a decision tree, which will be a succession of question and binary sorting that will enable you to have multiple groups at the end. So the advantage of decision trees is that the learning time is very short and that it's easy to understand. When you look at the result, you can see why each specimen was classified as it is. You can understand which question or test were asked and how the result of the test were assessed. So this is really good advantage of the method. Inconvenience is that you cannot have complex rules and that sometimes the frontiers are difficult to set. If we go back to this decision tree, it is a questionnaire to assess people when they are coming to hospital. So you are coming to the hospital because you have pain. Depending on where you have, in which part of your body you have pain, then you are assessed to a different specialist. This is easy to assess most of the time. Sometimes you have pain everywhere, and then this is difficult. But let's say, for instance, that you want to assess if you have fever or not. Where do you put the frontier between having a fever or not? If you have a temperature of 38 degrees, it's higher than normal, but it's still acceptable. So do you consider it as having fever or not? So this is not so easy to do. So this is one of the difficulties and inconvenience of decision trees, how to set frontiers. In decision trees, the space of the characteristic are cut in very sharp object. You have fever or you don't have fever. That's easy. Sometimes it's not enough to describe. Sometimes you need complex rules. And in order to implement those complex rules, you will have to go to neural network. So neural network is a good method because it enables to build complex rules. It does very well with continuous data, and it has a good resistance to noise. So if you have problems to identify the noise in the cleaning stage of KDD, it's not so important if you're using neural network because it will be good anyhow. The cons is that the learning phase can be very long. You have to have a large learning set in order for the results to be reliable. And it's very difficult to understand because the sorting of the neural network, the way specimen will be assigned to one group or another groups, it's in a black box. So understanding the decision and can be very challenging. So it's a little frustrating for experts because they have results and they don't know how they are obtained. So how does it work, a neural network? So a neuron in this context is actually a linear transformation which will transform an input vector into a number thanks to a scalar product. And then there is an activation function, which is nonlinear. It can be 1 or 0, for instance. So building on the input vector, which is the description of your data, you will obtain a number. And if you are building different layers of neuron, then you will be able to obtain different values each time that you will be able to combine and have a complex output vector. So each of the neurons is based on this structure. You have input data, you do a scalar product, and then you have this activation function. And each time you have a neuron, you have to set the right parameter to the weight of your scalar product and to the activation function. This is why you need a large learning set, because you need multiple entry for each parameter. So each time you add neurons, each time you add layers, you will need to set those parameters. So learning sets have to be very large if you want to have complex neural network. And as you can see, it's easy to understand the meaning of input neurons because the scalars, the vector that you use as an input, they are representing your real specimens. This number represents things that you can measure. It's the age of the people, the kind of medications they are receiving. But once you are here, the value is not related to anything real. It's only a number. And when you use number to create new numbers and so on, then you lose the relation to the real phenomenon. That's why it's so difficult to understand for experts. So this is really not a black box because you can know every function. You will know the weight that are used, but there will be no relationship to the real phenomenon, so it's more of a gray box, which are not so easy to use for experts, field experts. It's quite clear for a mathematician what it is, but then you lose the explanation to the field. So there is no physical explanation of the result, which might be frustrating, but enables you to build more complex relationships and obtain interesting results.